My name is Joshua Ott. I'll be talking about ROS, Robot Operating System, version 1.
ROS is a set of software libraries and packages made to ease the development of robotic applications. You can think of it like a distributed operating system. The core of ROS is the ROS master communication layer. It's actually called ROS core. In the robot operating system, one builds packages. Packages accomplish tasks for the robot. These packages are built out of nodes, and nodes are the smallest computation unit in the ROS system. Each node can publish or subscribe to topics. Topics consist of messages sending data or other information in between nodes. One of the unique things about ROS is that the nodes can be written in any language. They don't need to all be Python or C. So long as the messages they're passing follow the ROS protocol, then the ROS master can coordinate all of the different packages. In our robot, some of the packages we have are teleoperation that enables the joystick commands to be interpreted via the Ackermann mux, and those commands sent to the motor and the servo. There's a package that controls the LiDAR on top of the car. All of these packages run on Ubuntu on the car's computer and come together to give the car the functionality that we need. Here we're running the teleoperation command along with the slam command in order to activate the LiDAR and start mapping the environment. Now RViz connects to the topic that publishes the map data and the car's localization. Those pink floating dots are a point cloud generated by the LiDAR on top of the car. As the car moves around, it slowly builds a map of its surrounding areas. From here, we would save the map, clean it up, and then import that map for the autonomous navigation. Thank you for watching this video on our cobot robot cars.
Hello everyone, my name is Isaac Jacobs and I will be demoing our AMR, or otherwise known as Cobot. We will be using a bunch of launch files today to launch specific nodes and topics on the AMR, and I will show you here in the next couple seconds on how to do that. Alright, so when we run the launch files, we first set up the teleop launch code, which is ROS launch underscore base teleop.launch, and when we run this, it's going to start a ROS master. It'll take a couple seconds to run. As we can see, there's a couple of descriptors, but we can ignore these. The LiDAR will start spinning, as we can see here. And this is because the real sense is not hooked up right now. But as we can now do, we can go to ROS topic list and run this, and it'll show us all of our topics that are being run through the launch file that we just launched with the Musher underscore base teleop.launch. We can also go down to ROS node list and run that, and it'll give us our nodes that are interacting with our topics through publishing and subscribing. And some of these topics even might publish and subscribe to other topics. Now we can shut this terminal down to launch mapping. using the Control-C command. Wait for that to stop. Now we can look through our, there it is. So to launch our SLAM, so our simultaneous localization and mapping, we launch this command. It runs the same nodes and topics as the teleop.launch. However, it now adds on the Hector SLAM nodes, and it runs those. So if we go into our other terminal, most of the topics will be the same, but if we go to our ROS node list, we can see that Hector SLAM has now been added. The Hector map server, the Hector mapping, the Hector trajectory server, the nav broadcaster, and the geotiff node, which we use to save the map. If we go up here in this, these were not there before in the other launch file. Now, if we go to another terminal and launch RViz, Control O, I have to go in and change the default RViz to another RViz workspace, which is in our catkin workspace, our source, our Musher utils, RViz, default RViz, and open. So we can actually see here that there is a map being built of the surrounding room that I'm in. The door is open, so that's why you can see this line right here. It hasn't fully mapped out this way because we limited the box size of the car, so how much it maps around it, because it causes latency. So if I actually go in to another terminal, which I have pre-opened here, this one right here, this command will actually save the current map in the geotiff file directory under the catkin workspace. So if I run this, it's going to say publishing and latching the message, press Control-C to terminate. We go back to the original slam.launch terminal, and we can see that the Hector map service was called, the map was called successfully, and now it was writing the geotiff plugins. After it finished, it successfully wrote the geotiff to the specific directory that I mentioned earlier, and it says how much time it took. So it's good. If we go into that directory, we should see something like this. So I go to Files, I click on Catkin Workspace, I go to Source, I go to Hector SLAM this time, I go to Hector Geotiff, I go to Maps, and now we can see the map that was just made. This one right here.
Hey, my name is Christian Chorus. I handled the machine learning and AI portion of our mobile robotics project for the senior capstone here at USF Electrical Engineering. And so just to talk about that, the goal of that was to implement a visual tracking feature using an object detection model similar to, so that the robots would have the ability to kind of see in a way that mirrors the way humans do. And because we're a stereoscopic species, it's really important. So for future collaborative robots, they're going to need to interact with their environment visually, see obstacles, see specific things they're looking for. In a search and rescue application, you might need to coordinate with other rescuers, you need to know where they are. So that was the point of all this. So the Jetson Nano is pretty well equipped for object detection and AI training. So we went with the PyTorch machine learning framework, which allows for a lot of different model architectures and different tools you can use. NVIDIA has actually developed a Jetson Inference API that allows a lot of different model types, specifically the ON and X structure to be converted to a format that is optimized for the Jetson Nano, increase your performance by a lot, because traditional machine learning and AI systems that are designed for higher power computers than a small portable computer often introduce a lot of latency on the Jetson Nano, and that was what we saw in earlier parts of the project. Before I started using the Jetson Inference API, we were getting very low latency, so by the time we're running a video stream from the onboard camera on the robot, so by the time the model had made a detection, the target, the other robot, had already moved somewhere else. So it was really important for it to be fast. And so that was where the Jetson Inference API really helped us. Using the PyTorch framework, I was able to create a custom data set of about 500 images of each of the cars, and use a base, we were using the single shot detection model architecture as a good trade-off between performance and latency. We wanted it to be accurate, but it was also really important that that speed was crucial. So that was why we selected the single shot detection. It worked very quickly with only a small reduction in accuracy, and for us it was more than effective. So training the base single shot detection MobileNet V2 architecture with a custom data set that I put together for the robots, we were able to train 2 separate models, and that actually improved our accuracy. So each of the robots, there would never really be a reason why it would need to see it or detect itself. So it was a little bit more efficient to create 2 separate models for each robot to have, where each robot is capable of detecting solely the other robot. And so that allows for collaborative navigation for them to follow each other. If they're looking for another robot in a space, they understand when they see it. C being the detection is made with a confidence threshold of over 98%, because everything in machine learning is statistical inferencing and predictions based on the data it's been trained on, looking for some of those connections and then making a probability estimate of whether or not the object you're looking for, in this case a robot, is in that specific spot of the image. And so doing this, we were able to get to run this model with a latency or frames per second of about 45 frames per second. That was our typical speed, which is more than enough for what we need. It worked well. And then all the data from those predictions, it draws a bounding box around the location of the robot in the video frame, and then publishes those coordinates to the rest of the system for any node that wants to subscribe to it. So that object detection script in Python becomes a publisher node in ROS. So we have a couple of clips after that kind of show that working and how we ran that using the Intel RealSense camera on board each of the robots.